Right, so we'll continue our exploration of sound synthesis or speech synthesis in a little bit more technical way, and we'll consider one of the methods eventually that will teach us about filters and ways of synthesis. And one of the more powerful, although historically obsolete in some sense, speech coding techniques called LPC10. Although there is quite a recent work that uses LPC together with neural network to generate speech in more efficient way. So what is linear prediction, formants, and the spectral density? So spectral density, we will maybe just mention this. I will not exactly kind of explain the idea of spectral density versus spectrogram. But I would like to say that once we treat the signal as a statistical thing, that the Fourier analysis has to be kind of reconsidered, at least formally, if we want to think about this as representation of the frequency contents. If the frequencies are random parameters, I mean, if the signal itself is a stochastic process, frequency is going to appear and reappear in different probabilities. And then if we do the Fourier analysis, every outcome of a Fourier will be another random snapshot. So we need to average these things together. And so if we estimate or we consider the spectrograms as a random process and we do averaging, that becomes power spectral density. Even though I put this originally on the syllabus, the formal definition of spectral density will require a little bit. It would require a little bit too much time. So I think we can kind of explain the idea of spectral density just by the idea that if we pass a noise through a filter, that noise will have certain statistical properties, certain correlations that will be manifested in the distribution of frequencies. So from now on, when we talk about spectral shapes, you need to think about them as some kind of a mean energy or an average energy for different frequency bands rather than one snapshot of a 50. So by saying this, I kind of like relieve myself from, at least right now, trying to formally define spectral density or power spectral density. But you should be aware of the fact that once you move from deterministic signals to random signals, the whole idea of spectrum has to be slightly modified. So the first underlying concept that we already seen in the vocoder slides, and it's much more dominant here once we start actually modeling these things mathematically, is the idea that speech could be considered a source filter. So what is the source filter? The idea is that you have your vocal folds that, they have your basically vocal cords, and by passing the noise through these vocal folds, they start flapping and they create your glottal pulses. And this signal, if it's voiced, if it's unvoiced, it's just kind of a noise like going through an open vocal tract, open vocal folds. And then this signal goes into the vocal tract. So what is a vocal tract? It's basically the cavities of your mouth and nose. And by moving your mouth, you actually change the resonant properties of your vocal tract. And so the assumption in source filter model of speech is that you have a sound production mechanism that is an excitation that passes through a filter. The rate this filter changes is about 20 milliseconds. And the idea is that sources, the glottal pulses filters are the vocal tract. And now what we see in the output is actually the waveform, the speech. And in order to kind of go back and invert this model, we have to separately estimate the source parameters of the pitch and the filter coefficients of the spectral envelope. And this spectral envelope, which are the resonant properties of the vocal tract, are efficiently estimated by a method called linear prediction or linear prediction coefficients, linear prediction coding that we'll talk about towards the end of this class. And now the important thing is that the peaks of your envelope, they determine so-called the speech formants. So we'll talk about what the speech formants are. Kind of what this part of the figure shows. I want to kind of like be able to point this out because it's important. The idea is that if this is the overall spectral shape of your vocal tract, these are kind of broad resonant properties. You have kind of a range of frequencies around R1 that are amplified, another range of frequencies around R2 that are amplified, okay? They remain invariant to the pitch. The pitch itself are these harmonics, right? These are the partial. This is like the first fundamental, the second partial, the fundamental, the first harmonic, second harmonic. They're all multiples of the initial pitch, right? And if this is a low voice, like a male voice, you'll have a low pitch and you have all these harmonics. While in high voice, let's say female voice or children voice, you start with a high frequency, your note is high, and then of course the partials are spaced much farther apart. But once this signal is passed through this filter, it now has this extra shape, which kind of corresponds to the areas where the frequencies are amplified or where the frequencies are dampened. Now, why we use this kind of a shape rather than flat? Actually, for many practical purposes, we'll start with equal energies on all frequencies, or so-called the pulse train. We will not really prove why a set of pulses will have all partials equal amplitude, but the normal vocal tract has this kind of a decaying shape. So you can either incorporate this overall kind of de-emphasis or this kind of a shape into the filter and start with a flat set of harmonics and slightly tilted filter. But the important thing is that if this is invariant, this is kind of like depends on the voice, this depends on what you want to say. And this shapes eventually the overall spectral envelope of the speech that we observe. Of course, that speech will have also the partial structures of the harmonic structure based on the voice of the person. So what are the speech formants? If we think about now a spectrogram here, which is the usual way we consider time and frequency. And if you remember, we spoke about wideband spectrogram. So we don't see here the partials, we don't see here the frequencies. We see kind of these broad, smeared or smoothed out areas of where the energy lies. So the spectral peaks that we have seen here, right, this R1, R2, they correspond to these dark areas. Now you have more than two formants. This is F1, F2, F3, F4. But if we just take the first two, the formant 1, formant 2, and this is a spectrogram analysis of E, and this is of A, and this is of A, okay? And we just observe the first two formants as we go from E, A, we can plot the phonemes basically, or the vowels in this two-dimensional space of formant 1 and formant 2 here. So each pattern like this, if we ignore what happens in the higher formants, is a space, is a point in this space. And you can see that, for instance, E, okay, has a low frequency. The first formant is low frequency, and the second formant is high frequency. So if you locate it here, the first formant is low frequency. It's what, about 200, 300 hertz here. See, this is 4,000, so this is kind of in the around 300 hertz. And then the second one, right, somewhere halfway, so it's probably around 2,000 hertz. Yes, so 2,000 hertz here, okay? So this formant that we see here is represented as a point in the formant space, which will be some like formant 2 around 2,000 or 3,000, and and the first formant around 300 or 400 hertz. Okay, and then as we move towards A, okay, you see that both the first formant moves up and the second formant moves down, and we end up somewhere here. Okay, you can actually create a table of formants as a phonetic transcription of the vowels, and kind of relates to the speech to text example that we've seen from the Neville Laboratory report. To have, of course, much more reliable production of formants, we might want to use 3 or more formants. So this would be the F1, F2, F3 would be the third peak, and they have certain width or standard deviation, but this is kind of a typical table that one would use to generate these filter shapes if we want now to produce speech. So moving on, how do we generate these filters? So this is kind of a good opportunity to a little bit dive deeper into signal processing, the filtering part. If you remember when we spoke and we talked about the convolution theorem and the idea that a filter is basically a signal that is convolved with another signal, we spoke about so-called forward filters. Basically, this is what we see on the left part. We spoke about filtering as a process of taking a signal, multiplying this by some scalar. So you have an amplifier here. T here represents a delay, okay, which we usually would also, usual notation would be Z minus 1. You delay this by one sample, you multiply this by another coefficient, you delay this, and you add everything together. So this is our usual filter. That's the filter we have seen in our previous lecture notes. Okay. We can also think about another filter, which is so-called an autoregressive filter. And this filter basically is a feedback. It takes your output, it delays the output, multiplies this, and returns this back. It takes 2 steps of a delay of the output and returns this back. So the forward is the B, the feedback are the A's here, and the forward path is the one that actually adds up sinusoids. It can create phase cancellation. It can actually eliminate signals from the original signal, while the feedback creates resonances, because this is a signal that kind of comes back and goes in the loop, and it can actually explode. If you get these feedback loops that suddenly, you put a microphone next to the speaker and get this whoop, that creates a feedback loop. So it's very important that these filters are stable, that they don't explode. Now, mathematically, this is actually written in a way that you have kind of 2 sides of filters. You have the filter working on the Y's, and you have a filter working on the B's. The simplest one, so-called the one-pole autoregressive filter, and I'll explain why it's called the pole, it can be expressed this way. You have your output, which is the sample at that moment from the input times B0. So we basically don't have anything except for this path. And then we have only one loop here. So basically what we'll be looking at is just, this section. We have this and we have this, okay. So this is the filter we'll be describing. And in this filter, what we have is the output here, Yn, is the input times B0 plus 1 delayed output with an A1, okay? And in this case, we just need to make sure, because here the A is with a minus, so we can change the sign here. But this is the expression, this is the equation that you can take a signal X, and after entering the first sample in, you already have Yn, and then you can keep on going with, you would always have the Yn minus 1. If n is bigger than 1, you can kind of run any signal X through this equation and get a different signal Y. If we use a Z transform, again, without us going into detail what it is, you actually, if you remember, delay by 1 step creates a Z minus 1. Here, you can write this as a Z transform. It's actually exactly the same if you would run this with a Fourier transform. Now, why I needed to talk about the convolution theorem. This is because now you can think about this idea that X and Y are related in frequency as a filter. So if we now move X on one side and Y on the other side, you have a relation of Y equals H times X. So if we move everything to the other side here, right? So we'll have Y plus A 1 Z minus 1 Y on this side and B0 X here, and then we divide by this. This is the transfer function of this filter, and I will kind of show this a little bit later in more detail. But now what we have, this is the relation between, in a frequency between Y and X. Actually, if you take a signal X and you pass it through a filter that has a response H, you'll get an output Y, okay? And if we switch the Z to be a Fourier transform or plug it on the unit circle, this is the frequency response of the filter. This is how, the graph now, you can actually plot this filter and you can see where, how it changes the output, or what are the energies for every omega. Every omega I plug in, you have this expression here. So this transfer function, why it's called poles? Well, the idea is, and we'll show this in a second, the idea of a pole, but I want to define this already here. We said that the Z transform is just a mathematical trick to take time, these difference equations in time, and translate them into frequency domain with these delay operations, and it becomes a polynomial in the complex domain. These polynomials have roots. You can solve them, basically define the zeros of these polynomials. So whatever is the root on the top, if the filter is written in such a way, rational filter, that's how it's called, the roots of the denominator, so you have the numerator and the denominator. The roots of the bottom part here are called poles. Poles are basically roots of the denominator. So moving to the next slide. Okay, I think I have to erase and then we can move. Okay. So now we can actually go and synthesize things with an AR filter. I skipped the slide, so let me kind of just bear with me for a second, just about the theory of this type of representations of filters, because this is kind of optional, but I want them to explain this graph. Okay, so we said that a filter is a polynomial in the Z-plane, and if it's written as a difference equations where you have X and Y's on two different sides of these difference equations, you can write this the transfer function as this ratio. Okay, so this representation of a function is very powerful, because now you can see that this is a polynomial. You can write this as basically find the roots of this equation. You can rewrite any polynomial as multiplication, where each one will be the specific root. You can also write this way, okay? And now these would be the zeros and these will be the poles. So the Q and the P, the Q will be the values of Z that equal to Q will make the 0, and the values of Z which equals P will be divided by 0, so they'll be infinite. So there is this very elegant way kind of to summarize why we want to have this rational representation of a filter, or a filter as a ratio of two polynomials, is because now we look at these P's and Q's, and they're complex numbers. We can actually put them on the Z-plane, P1, P2, or the zeros, Q1, Q2, okay? But we actually care about the frequency response, which is on the unit circle. I know there's a lot of material, because this is really, something that is pretty advanced in signal processing. But here is kind of the concept, because we provide you with a notebook that actually designs your formants by placing the poles in certain positions. So what is the meaning of this diagram? Okay, if you think about this diagram as basically positioning a filter response with the P's and the Q's, you can measure the filter amplitude response in this pole zero plane, that's what it's called, by looking at basically the distance. So every point on the unit circle is far from each pole or from each zero to a certain extent. So whatever the poles are inverse distance, right? So the closer you are to the pole, you divide it by a smaller number, so you have a peak. Okay, so when you go on the frequency and you land at a certain frequency closest to the pole, this is where your amplitude of the frequency response will give a peak. Okay, well, if you get close to the zero, this h will be small, okay, and this will be where you have a dip. So as you go through the different frequencies, if you have a filter and you know what are the poles and the zeros, you can actually calculate by calculating these distances and these distances and doing this geometry, you can trace the amplitude response of your filter. So when we do the synthesis with such a filter, you're actually provided in the homework with these two functions. You know, one is the excitation, which is a way to generate a set of pulses, and we use the sum of cosines just to create a harmonic structure with multiples of some basic frequency. Okay, and then what else? So you have to enter here your pitch, okay, and you'll create all the partials and harmonics, and then we filter this with this filter. And what is this filter? This filter is actually this rational representation of B's and A's. It's exactly this. You have the B's and A's, or here, you know, the top is the B's, the bottom is the A's. So you create this set of coefficients. In our case, the B is really just a zero, okay? And then the A's will be a set of poles which we calculate here. So what are these poles? If we want to create a peak, a spectral peak, okay, at frequency, at a certain frequency f, okay, what we want to do is basically we need to find the radius of the pole, okay, and the bandwidth, okay. So first of all, the angle, okay, the angle is 2 pi f divided by fs. So because we do everything in frequency in hertz, this is relative to your sampling frequencies. So it's between 0 and 1, this ratio. So this angle is theta, okay? If you want to peak at frequency f and your sampling frequency is fs, this will tell you what is this angle, okay? So this pole will have to be at this angle, okay? And this is why we put it here, okay? And then the question is, where is the radius and how far it should be, okay? And the idea is that if we assume that the bandwidth is 0, I mean, this is really kind of a hack of, it's just hacking of like where to locate this here, where kind of the concept is that if the bandwidth is 0, you put it on the unit circle, R will be 1, which is actually not true, because if it's here, it should be infinite. So the bandwidth, and then as the bandwidth grows, you go down and down. So the wider, so actually, yeah, well, bandwidth 0 is infinite. So it kind of does make sense, sorry. So if the bandwidth is 0, you put it on this pole, but the bandwidth 0 means that you have really like spike here, right? This little peak, this kind of a shape, bell shape, will become really a spike. And if you go down and your bandwidth becomes very big, you kind of go down here, and this becomes very smooth representation of the peak. So this is the control of how wide this this bell-shaped or whatever, this kind of a bell-shaped curve is, and this is where it's positioned. And once you have this r and theta, you basically just translate this to complex coordinates. Okay, so this is the radius, this is the angle, and this becomes a complex number. Now, what we do is we just put all these poles, and for reasons that you know, I'm not going to explain too much in detail, because our filter creates real numbers, or the signal going into the filter will also, it's a real signal and the output is a real signal. One can show that for such filters, every pole has to have a conjugate pole on the other side. Okay, so this is why we have the conjugate poles. So we have actually a double number of the poles. So if we want 3 formants, we need to have 6 poles. If we want to have 4 formants, we have 6 poles, where 4 will determine the shape and the other 4 will be conjugates that we just matched here. So just take this as a fact, but this fact really relates to the fact that the filter has to generate real coefficients. The coefficients the coefficients A of the filter are real numbers. This is why the poles will be conjugate. So if we put all these poles together, we have this function in sci-fi signal processing that now takes the 0 and pole representation and translate this to filter coefficients. This is the time frequency. So this magic, of course, we're not explaining this, but this is what it does. You know, by taking these things, it actually generates the actual filter coefficients here. Okay, it will generate you A's and B's. Now, once you have that, now you can take your signal, which was generated here, you filter this, and this becomes your speech signal. So kind of trying to see if we can kind of like look a little bit more get some insight into linear prediction. This is a little bit, you know, this is optional. I mean, it's not part of really the homework, but the LPC is a powerful method and it exists in LibreOsa. So what you can do, I mean, if we want now, instead of generating synthetically, right, we can basically take our formats. We can take this table here, right, and we can, according to these frequencies, we can actually generate our poles and zeros. And with these poles and zeros, we can generate our filters. And with these filters, with the speech signal, which will be the glottal pulses, we'll create our vowels. Okay, so this is kind of going from speech, if you want, or from phonetic transcription and the formant positions and frequency to actual time signal. But can we go the other way around, and that'll be more of a speech to text, or finding the formats for a given signal. So one very elegant method to do this is called linear prediction. And because this allows us to basically take a signal and find the filter that corresponds to the formants. This was used as a way to encode speech and do vocoding for transmission purposes, for communication purposes. So what is a linear prediction? Okay, just as the name suggests, this predicts the next sample by linear combination of past samples. A little bit like a Markov model, if you wish, but it has different, I mean, it takes P samples into account, okay? And it tells us that the next prediction will be this regression, basically, of P previous samples with these coefficients, and that will be our next prediction. The convention is to use them as negative, and I'll show you in a second why, but this is just a convention. You know, you can consider them, you know, can define A with a minus inside. So this is our prediction. And now we can actually think, what is the error between the true signal and the prediction? So the reason for using minus here, because if you plug this here, you will get basically this kind of a positive looking expression, where we even took the index instead of 1 here to 0, And we use the convention that A0 is 1 because A0 multiplies this. So we have yn and the rest of the predictions from Y1 to P. It gives us this nice expression, okay? So again, it allows us now to think about this whole process as a filter. Okay, we have the excitation here going through a filter and creates our speech signal. Here we kind of use Y as the speech and the input, instead of X before, we actually call it E because E is kind of the error signal of the prediction. So it's kind of inverting the problem. So if you have the error signal and you pass this through this filter, you'll get back the Y. If you check the equations here, you can see that, you know, it takes some time to kind of play here with the math, but if you kind of go carefully through this thing, you will end up with this expression, which is really exactly the same as what we have seen here, just we had first order, okay? We have P equal 1, so this is what you get here. If you go and do this for prediction of order P, you'll have this kind of an expression. So what we have is kind of a filter now that takes an excitation, takes some error, okay, multiplies this by sigma, which is the variance of that error. If we usually use E, we assume that E has a variance of 1, and we multiply this, so we scale up that variance. Then we pass this through this filter in this kind of autoregressive way, right? So this is 1 minus A because the whole filter together is A. This is just a 1 minus because we passed the Y directly. So just check, take your time just to make sure, validate that everything here is correct. But this is the filter that will generate our Y. And in LPC, in LibreOssa, you can basically take your speech. You can take now recording your speech. You decide your LPC order, so it will create as many formants. It will basically create half of the formants, 5 formants. And you will get your coefficients A, okay, estimated by one of the ways to solve this. So it's an optimization problem. There are several algorithms that do this. It's a mean square kind of optimization problem. But if you plug this in, you have a solver, you get A's. And then how can you actually estimate your new signal? Well, here's our filter again. We said 1 minus these coefficients. So this is 1, okay, 0, the 0 element of the vector is 1, minus all these coefficients, okay? And we filter our signal with this, okay? And this becomes our estimate, and the error, as we said, is the true signal minus the estimated signal. We just need to shift this by 1 sample because this is a prediction of the next sample. So if you try this out, you can see how well, given a speech, you approximate your signal just by predicting the next sample from the previous samples. And it's actually pretty amazing that these things work. As a conclusion, I would like to relate this to the speech synthesis and the diagram that we've seen from the Bell Labs, the first voter example. If you remember, we mentioned that the lady was a typist, right? She had a switch that would go from noise to a pulse train, the buzz, and there was also a pedal that was controlling their pitch period. Now, I kind of didn't mention why we have noise. So this is for pitch sounds, and this is for unvoiced sounds. And the idea is that we can speak with a voice, or we can speak by whispering, and we still can modify our, you can still understand what I'm saying. So I can say this sentence, right? A LPC model of speech, and I'm using my voice. And I can say it in different pitch. I can also whisper that. I can say LPC model of speech. I hope you can hear this, and I think when I push the air, I got the little pitch going. But still, you can still speak without that pitch. So this is the whispering. We still modify our vocal tract, and these are the LPC coefficients. So this actually became a way to encode and decode speech. You can think about this like a little speech fax machine that takes speech, translate this to these filter coefficients that change over time. So one thing is that you do need to update your pulse and zero. Well, actually, it's only the pulse and the energy. So you have the LPC coefficients. You update them at a certain rate. Okay, so you still have 20 milliseconds update rate, and then you have at 2.4 kilobits per second. This is the encoding bit rate. And again, this is not a class about communication or compression, but I think it kind of gives you a little bit of that perspective. It's very kind of real numbers. It's a reality check. So what we have 28 bits that we allocate sending the LPC coefficients, the filter coefficients. We have 7 bits to encode the pitch, okay, basically how high or low it is. We have 3 bits to encode voiced, unvoiced. Why it's not in 1 bit or 3 bits, I'll have to remind myself. You have 6 bits to encode the energy, that's sigma coefficient, and something about spectral amplitudes. So you combine all of that representation into 48 bits at the rate of 20 milliseconds. You can do the multiplications. So you have 50 of them. You get an encoding of speech in 2.4 kilobits per second. Okay, very efficient. Again, this is not exactly an encoding of the error signal. It's really approximating the error signal into either a pitch, an ideal pulse train, or switching this to noise. So here there is really a lot of lossy compression going on, because if we pass the original error signal into the filter, we'll generate the original speech. But here we kind of condense this to very small representation, and we have to send the filters. And if we want to increase the quality, we can have a little more details about the pitch variation and slightly more of the RMS energy and so on. So this kind of gives you an idea of kind of extracting features of a model. I mean, the one thing to keep in mind here is that this is really a model-based approach. We assume something about the speech. We assume this is a source filter model, and we use a lot of signal processing knowledge here to create this this representation. But I think it's I don't know if it's called eye-opening or ear-opening, just to realize that with filters and the idea of pitch that we kind of discussed before, like the notes that you're performing with the harmonics, or noise, and spoke about the difference between noise and pitch, and filtering this, you can kind of quite well approximate a speech signal by generating separately these peaks or these pitches or noise here, these filters, and then running them in a variable manner to get a very efficient representation of speech, and generated this in a compact way, and then create your text-to-speech system if you want. But again, I mean, this is kind of the state of the art before trying to explore more elaborate statistical models that would do this by more general filters or more general networks that would generate eventually, instead of the LPC as a speech, you will actually generate the MEL spectrogram rather than separately the pitch or the noise and the overall picture. So if this is the representation that the filter gives, and the pitch will give you the lines here, a lot of the modern models will actually generate for you a spectrogram, which is also very much dependent on the speaker itself. It learns the speaker characteristics and the rate, the prosody. But as far as human engineered features and human engineered way of compressing and understanding speech, this is pretty much state of the art. Okay, so I'll stop the recording and see if we have any questions.